We talked about two-dimensional steady-state problems. That was actually the most extreme case that we can go for a steady-state problem, like a two-dimensional problem, where you have temperature varying along both x and y directions. We had a plate, rectangular plate, with the dimensions a, b, and we were keeping 3 of the edges at the constant temperature T0. Well, actually, all 4 edges was constant temperature, but 3 edges were at the same temperature T0. One edge was at some temperature, which is a function of the position Tx, and we solved this, and we came up with an equation after we applied the shell balance. We came up with an equation, governing equation, which is basically Laplace's equation. This is called Laplace's equation, if I not said it before. So let me write it. Laplace's equation. Probably you have seen this, I'm sure you've seen this in analytical methods class. We solved it analytically using separation of variables. We did not non-dimensionalize the equation, but we changed the variables from t to theta just to make the boundary conditions simpler. Instead of t zeros, we were having zeros in the boundary condition, 3 of the 4 boundary conditions. And then the simple boundary conditions gave us the theta as a sum of functions, which are basically f of x times g of y, and that's what we got. And we're able to find the an values, the constants, the coefficients of this series sum using the orthonormality relations, right? Okay, let me just make a note here. If Rn is 1, it's called orthonormal. Normal means normalized, so it's giving actually 1. For any Rn, other than 1, we call them generally orthogonal. So that's the difference between the orthonormal and the orthogonal. Okay, good. So that's a side note I wanted to make. Okay, good. So far, so good. We said we can use the orthogonality or orthonormality to be able to solve for the coefficients Bn, because when we take the integral Fn dx, then the terms which are not equal to n just vanish, but only the term that is equal to n survives. So we actually are able to pick up that particular term by using this orthonormality relation. Okay, so that's the mathematical trick that we actually went over. I'm pretty sure you also seen this in analytical methods. We also said that you can actually solve more complicated problems instead of having 3 of the edges at the same temperature, 2 of the edges at the same, but the other 2 are at different temperatures. We said you can decompose it in 2 solutions in such a way that you have 2 different set of boundary conditions for the 2, but each of them is like the one we solved. So you can come up with 2 different solutions, theta 1 and theta 2, and the sum of the 2 solutions is going to give you the sum of the original problem. So the solution of the original problem, because if you add the 2 solutions, we said that the boundary conditions add up, and also since the differential equation is linear, the sum of 2 separate solutions which satisfies the differential equation must satisfy also the differential equation. If you don't have any questions, I'm gonna continue with the next topic. Today we're gonna start talking about unsteady state problems. Unsteady state heat transfer. It's also called transient heat transfer. It means that the conditions or the system evolve with time. It changes with time. System changes with time. Okay. Maybe you have some, for example, some metal bar. You're heating from the two ends. You're keeping one end at T1, the other end at T2, and then the entire bar was at T0, for example. And for example, you're heating up the bar. Initially, it has a temperature profile like this. This is T1, T2, this is T0, for example. And with time, it's going to change. The profile is going to change, like, for example, this. And then the effect of temperature is going to penetrate into the inner surfaces and so on and so forth. And at the steady state, you're going to have something like this. This is T infinity. This is T is equal to 0. This is T is equal to T1, for example. Okay, so your actually temperature profile is going to change with time. Your fluxes might change with time, and so on and so forth. Okay, let's start with a very simple problem. Not that simple. I mean, it's not as simple as the first couple of lectures, but I believe it's much simpler than the previous class. A simple problem that we can learn, or by which we can learn about unsteady state heat transfer. This is called, I mean, the one that I'm picking up is, this particular problem is lumped analysis, or lumped heat capacitance. So why is this simple? Because now, as I'm going to show you, we picked a problem where the temperature does not vary along the positions, I mean, with respect to the positional coordinates, but only changes with time. It's like heating up of a metal sphere, or maybe cooling of a metal sphere. Okay. So let me particularly say temperature is generally a function of time and position in unsteady state problems. And we want to actually first deal with the problems in which t only depends to time but not x. So the question we should ask is, when can we assume temperature is a function of time only and not x? Okay. And to outline this question and to tackle how to answer it, let's go with the following simple example. Cooling of a sphere in stirred liquid. Okay, and here's the schematics that I would like to draw. Imagine that there's liquid here within this vessel. The vessel is adiabatic. You actually mix the fluid, so this is well stirred. Okay, and here you have a hot metallic sphere. You can also have a plastic one, but the reason why I'm putting there metallic is going to be apparent really soon, and it's basically related to our assumption that the temperature only changes with time. Ts, S for the sphere. Temperature of the fluid is Tf, F for the fluid. Okay, and for the time being, let's assume the temperature of the sphere is not changing with the position, but we're going to go back to this assumption and try to justify this assumption and see under what circumstances we can actually assume this reasonably. Now, here are the given parameters. Radius of the sphere is given as r. Density of the sphere is given as rho s. Heat capacity of the sphere is given as Cps for the solid. The reason why we're dealing with densities and heat capacities of the sphere, unlike the previous problems, is because the sphere is gonna cool down. So I need to take into account how much heat it's losing, and I need to relate the amount of heat to the change in the temperature of the sphere. In the previous problems and previous days, we didn't have such situations because our the bodies that we were studying were not changing their temperatures. Now, this time we actually need to mention the heat capacity and the density. And initial sphere temperature is Ts 0. Okay. And thermal conductivity of the sphere is K. Okay, let me actually align this thing. Okay, and the heat transfer coefficient, so basically these are the solid properties, or the numbers for the solid. And I need to give you the heat transfer coefficient. Let's take it as H. Okay. Volume of the fluid. Let's call it VF. Density of the fluid. Let's call it rho F. Heat capacity. The fluid. Let's call it CPF. Again, the fluid temperature will be changed also, so I need the heat capacity of the fluid. I need to relate the amount of heat gained by the fluid to the change in the temperature of the fluid. Initial temperature of the fluid is TF0. These are my fluid properties. Okay, so this is my problem. These are the statements and the given numbers. So here's the question. What is, sorry, or maybe find the temperature T of the sphere as a function of time. And then find equilibrium temperature T infinity of the sphere and 3, under what circumstance does T not change with respect to the position for the sphere, or along the sphere, say, or within the sphere. Okay, so we're going to actually check when our assumption is valid. Couple of comments. Well stirred, right? We said that the tank is well stirred, and this means the following. The fluid temperature TF is only a function of time, not a function of position. So for the fluid, I know the answer. For the fluid, if I mix it really well, then I can assume that at any point the temperature is not going to vary from point to point because it's well mixed, but it's going to change with time. It's going to heat up or cool down with time. That's a valid assumption just because it's well stirred. So let's actually think about this problem number 3. And what about the sphere? Under what condition can we assume the solid temperature is not a function of r, or the radial position. So for this, you can actually make a, let us do a rough calculation. Okay. And imagine you have the sphere, the surface of the sphere, imagine that it's at Ts comma S, and the center of the sphere, imagine that it's at Ts comma center C. And we want to actually talk about, or we want to actually understand when TSC is approximately equal to Ts comma S. Okay. So let's write down the Newton's law of cooling in combination with the Fourier's law of heat conduction. We say that the flux at the surface QR, capital R, is equal to minus K dt over dr at capital R. That's equal to H Ts surface minus T fluid. And let's do an order of magnitude estimation here, a very rough one. So I can basically approximate this thing as minus K. Instead of the derivative, I can use differences. The dt over dr is going to be in the order of Ts comma S minus Ts comma C divided by R. Okay, so it's something like this. Imagine it's your temperature profile is something like this, right? And I'm just assuming that the derivative or the slope here is approximately in the same order of magnitude as the slope of this thing, and the slope of that thing is basically the delta T divided by the delta R. So I can say that this is roughly approximately equal to H times Ts comma S minus Tf. Okay. So from here, if you take all the temperature to the right-hand side and all the other terms on the left-hand side, you will see that, or maybe let's take everything to the right-hand side. I just want to have the HR over K. So HR over K is going to be approximately equal to T SC minus TSS divided by TSS minus TF. Okay. But what does this mean? I mean, let's have a look at this thing. It's basically a number that I'm actually looking for, because you can actually think about two different cases. You have the sphere. You have the sphere. This is the temperature axis. This is the R axis. Okay. And imagine that I'm talking about two different temperature profile. One looks like the center, it's here. The surface, it's here. Oops. And the fluid is here. Okay. So imagine that the center temperature here, the surface is here, and the fluid here, and your temperature profile looks like the following. Oops. Okay. So this is your TF. This is your TS. TSS. This is your TSC. And the numerator is nothing but this difference, right? numerator, and this is going to be your denominator. On the other hand, if you have a temperature distribution like this, and if this is your numerator and this is your denominator, what can you tell about the two different cases? Which case actually I can make this assumption that the temperature is almost uniform along the sphere? What do you think? Which of the cases I can assume that the temperature is almost uniform along the solid? Right or left?
The second case, the right case?
The right case, exactly. So this case, I can assume T is a function of time only, not position. The T solid is a function of time only. And it's only when my numerator is much, much smaller than my denominator, or in other words, this number must be much, much less than 1, right? When is the numerator delta T much, much smaller than the denominator. Okay, so this means that this number HR over K gives me an idea, because that's something which is actually approximately equal to this number, right? Well, I'm not being exact here, but it doesn't matter. I'm talking about comparing 1 and 1000 or 1 and 1. Okay, so I'm actually talking about like orders of magnitudes here. So basically, if this means that, thus, if this number HR over K is much, much smaller than 1, then the solid temperature can be assumed uniform, changes with time only. Okay, and this HR over K is a very important number. HR over K is a dimensionless number. It's an important dimensionless number that tells us about whether we can assume T is uniform. Okay, and it has a special name. It's called bio number. And we can summarize it as BI is equal to HR over K. We call it bio number, and we abbreviate it as BI. Okay. Now a very important note here. Most students actually like to do this mistake, and that's why most of the professors like to ask this question in the exams. K is K here, K in the bio number, this K is the conductivity of the solid not of the fluid. Okay, that's very important. Although H relates to the fluid, the K is not related to the fluid. It's the conductivity in the solid. And sometimes we actually can write it as bio is equal to H R over Ks. Now you can ask me, oh, why would that be a problem? Of course, the K is the solid conductivity. The reason is because later we are going to learn about another dimensionless number, which is called Nusselt number, and in that number we have exactly the same formula, HR over K, but that K is going to be the fluid conductivity, and that's where most of the students actually confuse. So this is a very important note. Okay, so in order to memorize it, you just memorize the fact that bio number gives us an idea about whether our assumption of temperature is not a function of position is a good assumption or not. Okay, so the bio number, that's why we need to have the solid conductivity there. Okay, and it tells us the following: if K is large, for example, if it's really good conductor, for example, a metal sphere, what does it mean? It means bio number is large. Sorry, bio number is small. I'm sorry, bio number is small. Okay, better conductor it is, smaller the bio number is, so it's more likely that you can assume its uniform temperature profile. It makes sense because for metal surfaces, whatever inside, almost, whatever the temperature is inside is almost equal to the outside temperature, because the conduction is so fast that the temperature is equilibrated in a fast way, faster than the other heat transfer mechanisms like the convection on the surface and so on. But if you have a plastic or insulating material, it's not surprising that the center temperature is much different than the outer temperature. Okay. So that's about our assumption. So we actually validated our assumption, at least learn how to validate our assumption. Just find the H, K, and R and estimate bio number HR over K and see whether it's much smaller than 1. If it is, then you can assume that the temperature is a function of time only. Okay. Now let's go ahead and solve the problem. Okay. Page 2. Any questions so far? Okay. So let's do the energy balance in the sphere, because I want to have an idea about the temperature, how the temperature is actually going to change with time. So I need to relate the temperature to the heat inputs and outputs. But before that, I need to actually have a sense of what is going in, what is going out. And I need to do the energy balance in the sphere to understand this. Okay. So imagine your sphere is at the temperature T everywhere, here, everywhere. So we made the assumption that the temperature does not change with radius. Okay. And imagine that it's hotter than the fluid. Suppose it's hotter than the fluid. We're going to see that it doesn't matter at the end of the day. You can use the same formula for the case where the solid is colder than the fluid. So, okay, so let's say energy balance inside the, not inside, but let's say for the sphere. Okay, so let's say for the sphere. for the sphere. So my system is the sphere, okay? And I'm going to write down in minus out plus generation is equal to accumulation, okay? If there were any chemical reaction inside the sphere, it would be a really interesting problem, but let's make it as simple as possible because this is the first transient problem that we are solving. Let's not make it difficult. How about the accumulation? Any idea? What is the accumulation? 0?
No, no.
No, accumulation is not 0 because this is a transient problem. Things are going to change with time. But there's another thing which is 0. There's something else which is 0. It's the in. Because I'm assuming that sphere is hotter than the fluid. That means sphere is heating up the fluid, not the other way around. So the heat is being transferred from the solid to the fluid, not from the fluid to the solid. Okay. If I had the other way around, my out would be 0, but my in would be some number, positive number. Okay. And let's write our out. Our out is nothing but the heat flux QR at R times the surface area of the sphere, 4 pi r squared, right? That's my out. And the minus is this minus. It's coming from the material balance, or the energy balance. That's equal to the accumulation. Now, when I write down the accumulation, I should answer the following question. Is this the accumulation per unit time or just the total accumulation? It's the accumulation per unit time because on the left-hand side, this is per unit time, right? Because the flux was per unit time per unit area. You multiply by area, that's per unit time. So that's per unit time. So I need to write down the accumulation also per unit time. Okay? And the question is, what is the rate of change of the energy in the sphere? So the sphere has a temperature. It's going to have a thermal energy because of its temperature. So I'm going to write down d over d time, rate of change of its energy. The energy of the sphere is nothing but the Cp of the solid times the volume of the solid times the density of the solid times the temperature of the solid. You remember the formula Cp, mCp delta T? It's that one. Yeah. So this is mass of the solid. This is the heat capacity. This is the temperature of the solid, right? Although we should talk about the energy differences, even if you write Ts minus some T reference temperature, because of you're taking the derivative, this is going to be 0 because the derivative of constants are going to be 0. So you don't need to write down Ts minus T reference. You can just write down the Ts there. Okay. So this is energy or thermal energy of the sphere. Okay. Okay. Here you can say actually rate of in, rate of out, rate of generation, rate of accumulation, and so on. Okay. But I just want to make it simpler. Okay. So the entire thing is rate of change of thermal energy, which is the same as accumulation. Okay. Now from here, we need to write down the QRR The QRR is nothing but from Newton's law of cooling. The heat loss from the surface, QRR, is just H times T T solid minus T fluid. Both are functions of time. So you have basically minus H Ts minus Tf 4 pi r squared is equal to Cps is constant, Vs is constant, rho s is constant, and it's going to be time derivative of the temperature, right? There is one thing important here. Imagine that the solid is like colder than the fluid, and you're taking in minus out plus generations accumulation, and the generation is 0. Imagine that the solid is colder, so it's going to gain energy with time. So there's going to be input, not output. And for that case, you would write the input energy would be H times, if you want to take it positive, and you know that the solid has a smaller temperature, it would be H Tf minus T solid this time, times 4 pi r squared is equal to Cps Vs rho s dTs over dt. Okay, in that case, you will get this one. And basically, it's the same thing as this. So it doesn't matter, you would get the same formula. So that's my point. Okay. So there's no harm in assuming like one is hotter than the other, even if you don't know about it. Okay. In general, the formulas are actually, the governing formulas are going to tell you the correct behavior. Okay. Any questions so far? Okay. Now, let's actually make it simpler. So the Ts minus Tf is equal to minus Cps Vs rho s divided by H 4 pi r squared dTs over dt. Correct? And if you like, you can plug in the volume of the sphere in terms of the radius, but you don't need to do that. I mean, it's better to just leave it as Vs. And you can still, instead of 4 pi r squared, you can actually write down the area, surface area of the sphere, right? Instead, you can write it as Ts minus Tf is equal to minus Cps Vs rho s divided by H As dTs over dt. Okay. And let's call this equation 1. Okay. Let's do the energy balance for the fluid, but I need to make some arrangement here. Okay, so that I can separate my page in a nicer way. Okay, now energy balance for the fluid. Now, why do I need another energy balance? Here's the thing. If you have a look at this equation that we derived, the only unknown is not the solid temperature, but also the fluid temperature. So you need to have another equation for the fluid temperature, right? So you should use the same arguments, the energy balance for the fluid. In minus out plus generation is equal to accumulation, right? And there's nothing going out, but there's something coming in, because the solid is hotter than the fluid. Okay, good. And the in is whatever comes in with the Newton's law of cooling, right? From the, so since, I mean, whatever is out here should be fed to the fluid. So basically you have the same term there, H times area of the sphere times T solid minus T fluid, okay, is equal to d over dt Cp of the fluid times volume of the fluid times density of the fluid times the temperature of the fluid. And from here, you get Ts minus Tf is equal to Cpf Vf rho f divided by H As dTf over dt. Now I have two equations with two unknowns, two differential equations with two unknown functions. How can we proceed? So I want to make some simplification using the two equations, right? What we can do is basically we can get rid of this Ts minus Tf's, right? So by divide 1 by 2. So you get a simpler formula. If you divide 1 by 2, you cancel the left terms. You get 1 on the left-hand side is equal to HAS is cancelled, but you have the negative sign. CPS Vs rho s divided by CPF Vf rho f, right? DTF divided by, sorry, the other way around. DTS divided by DTF. So this gives us a relation between the TF and TS. We got rid of the time dependence. So at any time, if you know the temperature of the solid, this gives you an idea about what is the temperature of the fluid. Okay, and to solve this equation, let's call this chunk of constants as B, called B. Okay, and from here we get DTF is equal to B DTS, and let's take the integral, okay, from the initial fluid temperature Tf0 to any fluid temperature Tf, Ts0 initial solid temperature to any solid temperature Ts, and from here we find that Tf minus Tf0 is equal to B times Ts minus Ts0. From here, we write down the Tf in terms of Ts. Tf is equal to Tf0 plus b Ts minus Ts0. Now I can replace it in any of the formulas to solve for Ts only. So we can write, for example, this in, oops, here, right? What we get is the following. Ts, let's say, minus Tf0 minus b times Ts minus Ts0 is equal to minus CPS rho s over HAS dTs over dt, right? The equation number 1 came into this form. Now I need to collect all the TS's. Ts times 1 minus b plus some constants. So this is minus Tf0 plus b Ts0 is equal to negative CPS Vs rho s over HAS dTs over dt. Now I'm going to collect all the TS's on one side and all the T's on the other. But before that, I want to actually make this Ts, the coefficient of Ts1. So I want to divide by 1 minus b all the sides. So I get Ts plus minus Tf0 plus bTs0 divided by y minus b is equal to minus CPS Vs rho s over HAS 1 minus b dTs over dt. Okay, and you can actually, at this point, you can take the dt on one side and the ts is on the other side, so you get minus HAS 1 minus b divided by CPS Vs rho s and dt is equal to d capital Ts divided by Ts plus minus Tf0 plus bTs0 divided by 1 minus b. Okay, now we're going to take the integral of both sides from time is equal to 0 to time is equal to t. And when time is equal to 0, the Ts is equal to Ts0, the initial temperature. And when time is equal to t, let's call it Ts. And you get minus HAS 1 minus b divided by CPS Vs rho s times t is equal to logarithm of Ts plus minus Tf0 plus bTs0 divided by 1 minus b divided by replace the TS by TS0, TS0 plus minus TF0 plus BTS divided by 1 minus B. Okay, and finally, if you solve for TS, you get TF0 minus BTS0 divided by 1 minus B plus TS0 plus minus TF0 plus B TS0 divided by 1 minus B exponential minus AS, so subscript, H 1 minus B divided by CPS, VS, rho S, T. There you go. So this is the temperature profile. Do you have any questions so far? Let's call this equation 3. Okay, so we're going to talk more about this, and we're going to make sense of the formula by considering the special cases and dimensional analysis and all that.